Swayam Prabha. Digital India. Educated India.
So, it would be a nice thing to have a feedback at this stage. The rate at which the crowd is depleting, it tells us something, right? I suppose it tells you something as well, it tells me something as well. So, like how is it going? Honest answers welcome. It's like, yeah, a little fast. I should go, you mean to say that I should go a little fast? Oh, I see. So, I should go slow. Okay. Yeah, this is one feedback. Others? Yeah, you said something. Writing is too much. Meaning?
There's too much to write, too much to note down for the
See, this is math, so it's like you have to do something. It's like, as I said, algorithm is this much, analysis would be this much. That I cannot help, but your suggestion I can possibly, yes. Any more? So, how about the tutorial sessions? See, in mathematics, the point is, it's not that only you have to understand, you have to get used to it, right? So, getting used to this chart of bounds is not that easy. It takes quite a lot of experience to get used to using them. But there may be one reason for people not coming. It's like whatever is going on is not sufficiently interesting for them, right? Maybe. Yeah. Anyone in the hall now who was not there in the morning? Because it will be a continuation of what I discussed before lunch. So, anyone in here who was not in my morning session, right? Everyone was there. So, it's a, I presume it's a subset, right? Strict subset, fine. So, I mean, one reason I write, I mean, to answer your question, one reason I write is as because these things are mailed to you. I can go on like a storytelling session, right? Take this probability, take that, put that in Markov, put that in Chebyshev, the variance goes down, done. But then when you go back, you have nothing to read, right? That is one reason probably I am putting things down so that, and Professor Somasundaram has made arrangements to mail them to you so that you have at least something to, some reference points, because for most of them there is no textbook, there are some lecture notes, some papers, stuff like that. So, it would be a good point to have some references in front of you, and that is one of the reasons I keep writing. Anyway, so as you want me to talk more and write less, let me see, right. So coming back to so continuing from where we left in the morning. So, is the idea clear, right? Then again there will be a boring analysis, because theory is all about giving you guarantees, that I like without a guarantee an algorithm is nothing but a heuristic. The idea is clear? Any doubts? Any questions? Okay. So, what is now the algorithm? Choose a suitable hash function. Now, what do I mean by suitable here? I can straight away give you that hash function. I will not give you. What I do is I hold back giving you this particular hash function, and as we go along the proof, you would see that as the sequence of steps in the proof goes through, there would be a step where you need to jump from one step to the other, you would need the hash function to be of a particular kind. Otherwise, the proof will not go through. So, then you would understand that that is possibly the reason why the hash function was chosen like that. Okay. So, you choose a suitable hash function, its role is it takes members from the universe. Earlier I just wrote n, yeah, okay, fine. Now, to some value, maybe let me stick to a notation, yeah. Okay. So, the universe is this and you suitably map to some m. Now, you obviously understand your m needs to be greater than d, the number of distinct elements. So, make it suitably larger. So, this is a design issue and you know that this this hash functions has, so it is like essentially they would be kind of a polynomial over certain things, and then you take a mod of over this m, so that all values come in this range 0 to m minus 1. Okay. So, this hash function would be mostly something, what it is we will again see later, some mod m. So, you choose this suitable hash function. Now, this is your space. So, your space is required to store the hash function. So, Venkatesh in the morning possibly talked of a polynomial, right, as a hash function, right. So, to store a polynomial, what do you need to store? The coefficients of the polynomial, right. So, the coefficients of the polynomial would be in this range m. So, you would need roughly log m into the number of coefficients. So, we will see later on that the more independence that I need, the more would be the coefficient of the polynomial. So, then the polynomial would be of a higher degree. Uddalo, calculate problem. Vandermonde matrix, unique solution. K-wise. Right. So, space is required to store the hash function, and when if you read literature in randomized algorithm streaming, people who talk in terms of pick a hash function uniformly at random. What does it mean? Right. So, pick a hash function uniformly at random does not mean that you have a bag of functions and from which you just pick one function. So, it essentially means choosing these coefficients uniformly at random within a range, right. So, the moment you fix those coefficients randomly, you get a random hash function. So, most of the books that you would read or most of the literature you would read would say that choose a function, choose a hash function uniformly at random. It essentially boils down to choosing some coefficients of the polynomial within a range. Fine. So, now my algorithm is, once I have fixed the hash function, though I have not explicitly fixed it, I will later on show to you that how my proof dictates the choice of the hash function. So, once this hash function is fixed, what I do is, now the algorithm is pretty simple. Take the minimum and use the earlier idea. Now, when I say earlier idea, I mean actually this. Done? Pretty simple algorithm. The only space that you need is to store the coefficients of the hash function. Right. Now, I want to give a guarantee. Okay. So see, the issue is epsilon delta is one kind of guarantee. There can be other kinds of guarantees. Here I would give you a guarantee like this, that the number of distinct elements that you report is within a constant multiple of the actual distinct elements. So, say for example, d by some constant C1 and C into some constant C2 into d. So, your estimate would lie within this range, right. So, I will give you a guarantee like this that the estimate that you give is within a range, right. And I will try to bound the probability of this. Now, remember this thing that, so if your stream was this, and these were your hash values, but basically I would be dealing with not this many, but d many. Let us even rename them as A1, A2s. So, this is the set I would deal with. So, under the assumption that S is equals to D, the number of distinct elements is D. So, these are the values that I would be dealing with. And as a property of this hash functions, that it kind of distributes this. So, your earlier universe was this 1 to n, which has now been pushed to a universe of size 0 to m minus 1, but these values HA1, HA2, HAD, these D values are now kind of with high probability distributed uniformly in this range 0 to m minus 1, right. Now, if you look at these values, What are they? They are outcomes of a, what was your hash function? A randomly picked, uniformly and randomly picked hash function, right? So that means these values are random variables, right? Because your h is a random hash function, right? So the output of HA1, HA2, this would also be random variables. So the moment these values are random variables, I can even talk in terms of independence of these random variables. Now the level of independence of these random variables would depend on the level of independence that this hash function gives you. Fine. So I will come back to that later on, but that would be very useful. So what is the degree of independence that I need is crucial. That is crucial for space, that is crucial for the proof to go through. So as I said, I need some amount of independence. This I will fix later on as we keep working with the proof. Okay. So what do we show? Right. Mind you, this was your estimate t hat. So this is the theorem that we are going to prove. So, C you can assume 100, 500, something like that. My returned answer is this d hat, and I am going to guarantee to you that it is within a 6 factor of the. Now, as you would go along this, you would understand this, that these constants and these constants, they do have a bearing. So, if you want to make this too narrow, probability would go down, so on and so forth. Yeah. So, do you have any doubts about understanding this theorem before I attempt a proof? Now, in this proof, I will use a fact which Uddalok pointed out to you in a tutorial where he was doing this, there exists, and he was taking unions, right. This I will bring in here because there is minimum in here. Yeah? There you did maximum. Here also I'll use an argument similar to what you did. Okay. So, the theorem statement is okay, right? Let me now attempt a proof. First I show this part. So, I am looking at this m by min, in here it was this, right, less than. So, for me it would be better trying to prove within a range. So, what I would do is I would look into the probability of this side, this complement side, the probability of this complementary side, add it, take complements, fine. So, this is the way I will go about. So, that is the reason I am trying to prove this probability, that m by min to be not less than equal to but greater than is a low probability, 1 by 6. So, I am trying to argue that the minimum is less than m by 6d. So, that means the minimum is in this range, right. Right. So, that means I really do not care about all values. I am happy if there exists one whose hash value is less than m by 6d, and that exactly brings me into the situation that Uddalok discussed in that day's tutorial. So, I can take unions and then I can take a union bound. So, did you get this idea of the proof? Fine. So, now just I go through the motions. So, minimum is here if there exists an I such that HBI is less than equals to m by 60. So, I can write this probability as probability of there exists an I such that HBI is less than m by 60. It's like, okay. I think I can do it in here. So now what I do is I straight away jump to this sum. Mind you, my I runs from 1 to D because there are D distinct elements, right? And probability of HBI less than m by 60. Okay. Now this is nothing but, if you look into each term, probability of each term, HBI being less than equals to m by 60. So your favorable, your total possible case is m, and of them you have this m by 6d, I mean numbers in this region favorable for you. So the probability of each such term is m by 6d, you know, they suitably take a ceiling or something. So m by 6d by m, and there is a sum over d. So this is like d into if you do this sum, it would come out to 1/6 plus d by m. Okay. So I set out to prove less than equals to 1 by 6, but I proved it like not exactly, but 1 by 6 plus d by m, a little bit more. So I proved a probability. Fine. Any queries? Okay. Now on the other side, fine. On the other side, so if now the mean has to lie on the other side greater than, so that means each and every element should be greater than, that would get to a intersection, and as because you have independence, that would get to a product, right. So that would be the next line. So this would be, I'll show you why it is 6m by d. So mean is here if for all I HBI is less than equals to 6m by d. Oh no, sorry, it should be greater. Done. For all I, HBI greater than 6m by d. Now I have to figure out this probability. Now see, in the earlier case there was only one variable that was needed, right? You needed only one value, right? There exists I. Now all of them, every one of them has to be in that range. So I have to now be a little bit more careful. In the proof, I have not explicitly till now used this, how wise independence this hash function is, right? Nowhere it has been required till now. We will need this very soon. Be a little bit cautious when I jump from one step to the other step. Now, before I get into this calculation, let me point out to you one thing. So say for example, these xi's are independent, then what I could do? Add their individual variances. But if they are not, then there was a covariance term. Good. It's not that you are not understanding anything. I mean for general exercise, fine. Now, as because in here we will get to a situation where I would need Chebyshev. So, I would need variances of some random variables. Which are your random variables? The hashed values. Now, if these hash values are independent, now you know there is a level of independence, right? If I give you n random variables or n events, they can be two-way independent, they can be three-way independent, they can be fully independent, right? But notice this fact that in this bunch of n random variables, if they are just two-way independent, I am not bothered to get level of independence to be more. I do not even require three-wise independence. If these random variables are just two-way independent, then this covariance term would go to 0, because covariance is just pairwise expectation of x minus xi and y minus something. If I have this amount of independence from my hash functions, then this covariance term would get to 0, and I can now write variance of sums as sum of variances. This theory would actually force me to use a particular kind of hash functions. So, when I go through these calculations, you would understand that where exactly I need it, but the underlying theory is this, that at some stage I would have this, and I want to in that proof write it as this. But as you now know from this theory that just two-way independence allows you to write this. Fine. So, with this knowledge we get into the proof. What we have to prove is proof. Yeah. So, we now define indicator random variables for each I. So, probability of y equals to 1, that is greater than 6 by d. Why? It actually comes from here, right? So, what is, look into this fact, probability of yi equals to 1, that means this otherwise case. So, that means HBI less than equal to 6m by d. So, that means you are within this range. So, your favorable cases is 6m by d and your total cases is m. So, this probability is okay, fine. So, if that be the case, then your expectation of yi is also equal to this, and hence your expectation of y is greater than equals to 6. Now, for 0, 1 random variables, another interesting result holds. If you look into its variance, say yi, this is equals to expectation of yi square minus expectation of yi whole square. Expectation of yi square is nothing but expectation of yi, it is a 0, 1 random variable, right, minus whatever the expectation of yi may be, this is a positive quantity because this is a square. So, this is less than expectation of yi, right. So, this is a nice property of 0, 1 random variable. You can bound its variance with its expectation, and expectations are always easier to calculate than variances. So, these are like little tricks from probability that helps. Okay. Now, as your now I also want to write this. For this I need that two wise independence, right? Because a variance term will always have a covariance term, because this is now variance of a sum of 0 1 random variables. If I make it 2a independent, then this covariance term will go away, and variance of y would be nothing but sum of individual variances. Each one of them is upper bounded by their corresponding expectations. So, I can write this because of two wise independence. And you can also say that variance of y is nothing but equals to d of variance of any yi, because of the same thing. Now, see this part of the proof as it needed it. Now, I can go back and fix this, right. So, I need from this hash function just two wise independence. Then that theory actually goes through. So, if the hash function is two wise independent, then that means that the random variables that this hash function will throw up is two wise independence, and then I can play around with their variances in that way I showed. So, I will show you such nice examples how this in tomorrow's lecture, how I will show you that there will be algorithms where you require more independence. Okay. So, done, I have fixed variances and stuff. Now, it is just a Chebyshev. So, for all I HBI greater than equal to 6m by d. So, that means see, this is the reason I set it in this way. Mind you, yi is 0 when HBIs are greater than 6m by d, and your y is summation of yi's. So, if all of the i's are such that HBI is greater than 6m by d, then your y is also 0, right. Mind you, all of your HBI's, your i's are such that all of your HBI is greater than 6m by d. So, all of your HBI's are lying in this zone, and that was actually the trick of setting the random variable. It would not have worked out very smoothly if this indicator random variable was defined in the opposite way. This is a trick. So, each yi is 0 if that value is in this greater than zone, and I have defined my yi as summation of yi's, each one of them 0, sum is also 0. So, this is probability of y equals to 0. Agreed? Any doubts in this? And this actually, this y equals to 0 probability allows you to apply Chebyshev like this, because what I can now do is subtract y expectation of y from both sides, right. So, then on the right hand side you will get an expectation, on the left hand side you have y minus expectation y, perfectly in the form of Chebyshev. So, this is a trick that you should remember, that if you want to apply Chebyshev, getting to a form of probability that the random variable is equals to 0 is a nice form. If you can set up your math in this following way, such that it turns out that the probability of the random variable y is equals to 0, then Chebyshev goes through smoothly. All of these values have been fixed by now. So, this is variance of y by expectation of y square, which is nothing but 1 by expectation of y, which is less than 1 by 6. I have already proved expectation of y to be greater than 6. Variance of y has also been upper bounded by expectation of y. So, this was my part B. The earlier this union bound thing is my part A. So, this is my conclusion. The final result why? Because it is like complement event. So, 1 minus 1/6 plus d by m plus 1/6. So, if you work this out, this should be 2/3 minus d. Mind you, my goal was so this is where your m by d is possibly somewhere. My goal was to fix the probability within this zone, right. What I did was I fixed these two probabilities, took their sum, did a complement. That is why I have this expression. So, that is the final theorem. So, the algorithm is now pretty simple. Your theorem proof has dictated the amount of independence that is required out of your hash function. So, you use these two wise independent hash functions, make your stream just go through it, calculate its minimum and plug into that equation, you are done. Probably you have not studied a simpler algorithm than this, right. Two more things I wanted to do, because I would be here only this week. So, one was this heavy heaters. So, there the problem was is as follows, that you have an array or you have this stream and you want to figure out. So this is a variant of Mishra rise that Venkatesh Raman talked of. So you want to maintain or rather report. So your user would give to you apart from the stream say a number k, an integer, and you want to report those elements or maintain in a data structure those elements which has a frequency more than n by k, right. So this is actually a generalization of majority. So if you set your k to be 2 or something 2 minus delta where delta is very small, then that is a majority problem, right, because your majority is 1 which is more than n by 2. So here I am kind of generalizing this majority problem and I am asking you to report in the array elements which have a frequency greater than n by k. Again there is an impossibility result which shows that if you want to exactly figure it out, then again linear space is needed, you have to store everything. So again we will settle for an approximate variant of this. So this problem is known as heavy heaters. So I call them to be heavy heaters which have frequencies greater than n by k. So instead of getting the exact heavy heaters, I would get kind of the approximate heavy heaters. So that means what will happen is the elements which have a frequency more than n by k, that would be reported, but as because my space is limited and I would use hash, it will so happen that I will report some more elements which have frequency a little bit less than n by k, but not much, right. So that means I will not miss any sure elements, no false negatives, but I will report some false elements, but I will again give you a guarantee that those false elements are not much way off, they have a good frequency. So this will be one problem that we will study. The other problem is a classic paper, I mean which actually set up this field of streaming more. Now this was in somewhere in mid 90s, this is known as this Alon Matthias Szegedy frequency moment, second frequency moment problem. It is one of the most beautiful algorithms that you would ever come across streaming. So that I will do in the second half. So this is on the agenda for tomorrow. Of them, this Alon Matthias Szegedy is kind of a beautiful elegant algorithm that I would even if you miss everything, I think I would suggest that you attend that one. So you asked me to deterministically stop, but I went on for some time. So these are what is going to come up tomorrow. So those of your friends who have not come, if they are interested, ask them that this is the trailer of the movie for tomorrow. Okay, Professor, I stop here.